Pradeep Dubey is an Intel Senior Fellow. He's the director of the Parallel Computing Lab, a part of Intel Labs. There, he leads a team of top researchers focused on state-of-the-art research in parallel computing. The team is responsible for defining computer architectures that can efficiently handle emerging machine learning, artificial intelligence, traditional HPC applications for data-centric computing environments, and deriving product differentiation opportunities for Intel CPU and GPU processing platforms. Pradeep has made significant contributions to the design, architecture, and application performance of various microprocessors, including the IBM Power PC, the Intel 386, the 486, the Pentium, and the Xeon processors. He holds 36 patents and has published over 100 peer-reviewed technical papers. In 2012, Pradeep was honored with an Intel Achievement Award for breakthroughs in parallel computing research and was honored with the Outstanding Electrical and Computer Engineer Award from Purdue University in 2014, which is his graduate alma mater. He is also a Fellow of IEEE. More personally, I wanted to share that Pradeep and his team were among the first industry folks I interacted with as an assistant professor. I believe he and I met first on the boat of the HPCA 2005 banquet in San Francisco. At the time, his group was known within Intel Labs as the Applications-Driven Architectures group, and they were looking at how to accelerate code that performed recognition, mining, and synthesis. Remember, this was more than 15 years ago. Today, everybody's crazy about building accelerators to speed up machine learning workloads, but I guess some people start earlier than others. Over the years, I visited his team multiple times and always came away with great new insights. I would encourage young assistant professors to pay them a visit post-pandemic. So it is my privilege to introduce him to you today. Pradeep, welcome, and the floor is yours.
Thank you, Jose. Let me start sharing my screen now. You all see it?
Yes.
So, good morning, good afternoon, good evening. It's my honor to be asked to do ISCA Keynote. This is literally the conference I have grown up with in my technical career and learned more attending this and networking in here than any place else. I'm here to share with you my thoughts on machine learning and its implications for us architects. Just a small disclaimer up front, I'll often be using the popular term AI, which is naively perhaps, but commonly gets interchangeably used these days with machine learning. So let's start. What is, how do I look at AI? So I think of AI in these 5 dimensions, in terms of these 5 dimensions. The first and foremost, like Jose was just mentioning, is the expanding application space of AI, a class of applications for which AI is offering better solutions than the ones we have had so far. And these are primarily what I call outside-in applications. They're coming from outside, from data, and trying to understand, reverse engineer the model underneath. And then there is an aspect of how do we make AI more and more capable algorithmically, algorithms that actually make AI do this job better and better, that evolution of such algorithms. Finally, the 2 more important topics, more relevant to us, is how do we design better systems for AI, of course, but also I would spend time on talking about how do we design better systems with AI. And finally, we just have to make sure that this hen of AI continues to lay golden eggs for us, meaning it does good and keeps the planet a happier place. So in what you'll hear from me today, we would not have, I'll not focus much on the application space of AI, which is, even though we spend quite a bit of time doing that inside Intel, and also not have much time to talk about the ethics of AI. And I do have a couple of references in case you want to dig deeper of our work in this area. I'll spend some time on what is making AI algorithms so powerful and how do they, and what do we expect them to become over coming few years. But bulk of my time will be spent talking to you as to how do we, as architects and designers, design better systems to meet in the needs of AI, and how do we actually seek AI's help in designing these systems better. So moving on, let's start with the algorithmic space of AI, right? What makes AI so capable? And the best explanation I have, the way I have understood it, is from Professor Stephen Mallet, famous for his work on wavelets, or his discovery of wavelet approach. his video, and for everything that I talk here, you'll see a citation at the bottom for those of you who have become curious enough to dig deeper. He explained it very nicely. Often we talk about big data, but it's not just data. No matter how much data you have, the class of problems that we are interested in, the kind of functions we are interested in approximating, you cannot approximate them. Just imagine any high dimensional function, call it a d-dimensional function, and if you represent it on a unit sphere, and suppose you can purely just by having data, you can subsample that function to approximate it. And if you're able to do a look at every 10th point, for example, right, the epsilon become 1/10. Now you need 10 raised to 100 point to be able to approximate the function just simply based on data. And 100 is a small number. Most problems had dimensionality much more than 100, more like millions and billions. So there's simply no hope just because you have more data to be able to approximate function. The hope lies in what's noted at the left side, that these functions, these complex enough functions, we hope that they do have underneath a super sparse basis, super compact, efficient, deep representation, approximation of the dynamism in the function, which often represented as a dynamic graph. And the fact that we can compute it in polynomial time, not just what it is, but how it evolves slowly enough in time so that we can stay up to date. Now there lies the hope, and it turns out for more and more problem, that's actually true. So what makes ML effective, therefore, is our ability to find some such model structure, right, with all the implicit, explicit bias that we have, incorporating all the domain knowledge that we have. And if this model structure that we have in mind approximates or comes close to the invariant that we are trying to learn, the model structure that we are training is close to the model structure we're trying to learn of this high dimensional objective, then we will be actually quite successful, as has been seen with CNNs for vision problems, on attention networks for NLP. Then it's just primarily a question of how do we train quickly, and the training is a matter of balancing exploitation versus exploration, and so that you have a solution. And the better solution is in that fatter valley, right? Typical solvers tend to go into that sharp minima, and then you don't have the ability to generalize. Remember, the key point of AI is that I'm not looking for you, I'm looking for people like you. So I need a description of you that's generalizable, which is what happened in this fatter part of the valley. So that's what the whole training part of it is. So the combination of those two is what makes machine learning very, very effective. Now, what has happened is we constantly trying to learn these structures, quote unquote, right? And we have done very effectively for the 2D space or imaging, and that's how AI or deep learning did prove to be almost magical. We are hoping that we can, and now we can do the same thing for this high dimensional space that we now live in, the non-Euclidean space. And this paper that I've cited here and from Professor LeCun actually gives us good reason, good hopes to believe that we actually probably have a breakthrough of sorts. Thereby, we can actually look at graph the same thing that convolution networks did. Graph convolution networks would do that for these high dimensional in this high dimensional non-Euclidean space. Remember, graphs are hard because they don't have shift invariance. Subsampling graph, which we do routinely for 2D convolutions, is very hard. It's an NP-hard problem. And then ultimately, the stability of spectral methods are not stable for dynamic graphs, but graph convolutes have shown that property. So this interest in graph convolution networks or graph neural networks has skyrocketed. And we have done our own work in understanding and scaling these, and you see here the results. I'm sharing some of our recent results on scaling graph neural networks on large multi-node CPUs, and this is probably the best scaling that we have so far published, and best in state-of-the-art publication, state-of-the-art scaling figures that you see here for fairly large data sets. So moving on, where do we go from here? What we are trying to do now is, being an application lab, we are working always with people who are pushing that limits of science in terms of putting such theories or such systems to practice. And one such collaboration we recently announced with Mila, founded by Professor Yoshua Bengio. And our collaboration with them is to push the limits of science, understanding and putting to test such methods in the context of drug discovery. As you can imagine, drug discovery is a very hard problem because the space of molecules, again, that with the physics-based simulations, we can barely search up to 10⁹ molecules when we're looking for the effective one that will dock properly to make an effective drug. And we are hoping that the methods of machine learning will help us expand the search space to 10⁻18 molecules. Remember, it's way more than our current size of internet web pages, right? So if we can actually expand that search space, we should be therefore able to find much better molecules, much better drugs, much sooner. And that's the hope of this collaboration, working with them to also benefit from the latest and greatest compute infrastructure, exascale and beyond. Now, looking at this, I would also like to mention Professor Bengio's own vision of where all this is headed. Remember, machines are doing already perception tasks very nicely, right? And that means that these are the kind of things that humans, I highly recommend this Professor Kahneman's book, humans do subconsciously. What do humans do consciously? Humans do consciously decision making. So after you have perceived the world, you reason about it, and then you act. And that action changes the world again, so you have to reason again. That's sense, reason, act loop goes on forever. Now, humans do it very effectively. For us to be able to do that very effectively, we need to learn from humans, and we need to bridge this gap between neuroscience and machine learning. That's what Professor Bengio is suggesting that we may soon be able to do if we can figure out the quote-unquote consciousness prior, the inductive bias related to consciousness. And if it's represented nicely, if it's all about representation, if it's sparse factor graph representation, we should be able to learn the actions that human take, and that those actions will be local actions. Thereby we'll be able to generalize to these out of order distributions and understand how actions are taken and how distributions evolve over time. So this is pretty much the basis of where AI is today and where we expect it to be going, so that machines become better and better decision makers. So now let's shifting gear to the compute infrastructure that gets used for all such research. The data center compute infrastructure of today is rapidly evolving to these high dimensional learning infrastructures. What is that high dimensional learning infrastructure? It starts with data where this is, you're not doing any floating point calculation. It's simply understanding data, cleaning up data to prepare these some large data structure, which is typically a graph with billions of dimensions. It's too big a dimensionality for us to apply typical deep learning. So we have to apply sparse methods. And after that, the dimension is tamed down to a few thousands, where you can start doing ImageNet 1K like things. But the reality is that most of our attention has been so far on the rightmost side, where a lot of dense, irregular processing happens. But we are slowly shifting and realizing more of our challenge lies in the sparser processing. And in fact, even prior to that, there's no floating points, there the quote-unquote data management problems. So if we can do this effectively, and this is the kind of infrastructure that we're dealing with. Now, let's also look at how the workloads are evolving. AI is fastest growing algorithmically. Anything that grows so fast algorithmically does not lend itself to a special purpose processor. You have to capture it algorithmically first in software on a general purpose processor. Why general purpose? Because look at the evolution of this algorithm. It used to be CNN, and now CNNs have suddenly become something of many years back. Why? Because we moved quite a bit faster onto sparser models and GNNs, and now even newer algorithms. What are these algorithms like? So let's look at the spider chart of these algorithms in terms that architects like us can understand and relate to. What was exciting about CNNs, convolutional neural network, that they required systolic flop, that flop part of it quite a bit. And they had a very nice behavior otherwise. So you could actually build an accelerator immediately. There was a rush to build accelerators for speeding up CNNs. But look what's happened since then. When you move towards these newer forms of attention networks or graph neural networks or recommendation system, that spider chart that architects love to take the signature of that workload has changed dramatically, evolved dramatically over time, just in the matter of last 3-4 years. And when you put it all together, you can see that it looks very ugly, right? It has all kinds of elements. It immediately tells you that the way to win AI is to build the most balanced system, which balances flops with everything else, memory and networking. So flops have already become too many. It's the feed problem of flops that's really at the heart of our challenge. So how do we design better systems for AI? So let's now look at the 5 things that I have in mind for how we architects can design better systems for AI. The first and foremost opportunity is quote unquote feeding a compute beast. We already have enough flops. How do we feed them efficiently so that the flops actually happen? And the compute part of it is often talked about with these newer and newer. In fact, if anything, that the compute march is even steeper than last few years. And if you measure it in terms of training petaflop per second days, how many days it takes to train at certain petaflops performance, you can see that this growth is roughly doubling every 3 to 4 months. Nothing like that we have seen before, right? And what's less talked about is the memory capacity growth that needs to happen is also roughly similar. 10x per year is almost the same as a 3 to 4 per month doubling. Okay, so the two are growing significantly at the same time, and also the high bandwidth requirements, especially for workloads which are embedding dominated, such as the LLM. So how do we meet this need? So when you look at our traditional systems, we clearly have SRAMs, which are smaller in size, but you can get bandwidths up to tens of terabytes. We have HBM, which can give you single-digit terabyte bandwidth, but the capacity only goes up to hundreds of gigabyte, right? And or you have DRAM, which have more much more capacity than HBM, but still the bandwidth then is sub-terabyte. And or you have persistent memory, the capacity can go to terabyte, but then the bandwidth is pretty anemic. So there is a big sharp fall. And when you actually try to look at the working set, quote unquote, there is a power law in there for these recommendation type workloads or graph NN type workloads. And you see that the red line there is our approximation of the power law for the Criteo terabyte data set. If you look at the dark blue line, which is our projection of it, you can see that we are in the unserved gap territory. Right, so we're praying for a memory that's of that order of tens of terabyte, but the capacity needs to be high gigabytes to 10 gigabyte. Now, this doesn't exist today, but by the way, this is not a new observation. I was reminded of that exactly 10 years back at ISCA in a paper called Mogul's paper, right, with that Chris Hughes and Y Kitchen from our lab did then. The workloads then was a multi-program spec. So clearly the workload justification now is different, much more powerful. But what's missing then and is actually available now is not just the ask for it, but technology. Now we are actually have memory technologies that we're looking at which can deliver such a memory. That's the most exciting part of it. So moving on, the next big opportunity lies in compute. How do we raise the efficiency of compute? The dense computing happens at 90+% efficiency, architectural efficiency, but not the sparse compute. Deep learning is not sparse as in HPC sense, like one non-zero out of millions, but still has enough sparsity, like tens, right? So you have one non-zero for every 10 plus zeros. How do we become better at dealing with that sparsity? There lies a big opportunity for almost 10x potential for speed up in typical neural networks when you can benefit from not doing zeros, but only doing the non-zeros in input, in output, and in model. So if we can get better at handling sparsity, but the key ask here is that you cannot handle sparsity, the regular sparsity alone. The sparsity that's in there is unstructured. This has sparked a lot of interest, and as you probably see from this reference, that there is sharp growth in AI, sparse AI literature over the last 5 years, because it's a pretty nice problem that architects love to solve. We had our own such proposal working with Professor Tushar Krishna at Georgia Tech on coming up with such an architectural support for unstructured sparsity, and it does deliver significant speed up, like almost close to 6x. The key on the other hand is, which we still have to figure out, that how do we bring the cost down, the power, performance, area cost down of such an accelerator, so it becomes realizable in our products. This paper, by the way, earned us Best Paper Award at the last year's HPCA. And we have a collaboration. Professor Tushar Krishna is quite productive. There's a paper on accelerator, on compute, collective offload acceleration. Even at this ISCA, I think some of you probably attended the talk yesterday. So moving on, we have talked about compute. We have talked about feed part of it, north-south. Let's talk east-west. There's a major problem also when data moves from big data never resides on one node. It's always across nodes. So when data moves across nodes, we have significant efficiency problem. Why? Because the same irregularity that we're just talking about for the sparser networks begins to hurt us big time. The communication is irregular enough to actually have significant part of it exposed from compute. And when the communication intensity is high and it lands up and the latency of the network is high, we land up waiting and the latency gets exposed. And it happens increasingly now due to these irregular communications as the data size scales. So more and more, we are on the right side of this red dash scalability wall, and therefore beginning to feel the pain of scaling, because we throw resources, but the scaling doesn't happen. It's highly sublinear. What can we do? What's really holding it? What's holding it is historically, this problem has not seen much progress. The network bandwidth, as you probably see from this plot from Professor Panda's keynote, has improved. But what has not improved is latency. Latency of small messages is stuck at around one plus microsecond, more than a microsecond, for small messages, MPI protocol end-to-end. And interestingly, Fabrizio Petrini, who's on our lab, his 2003 paper shows the same microsecond latency with that many years back. So over last 17, 18 years, there's not been much progress. And there's probably not going to be much progress over next few years also. Why? If we stay this route, but there is light at the end of the tunnel. The biggest problem that we're currently facing is the fact that off-chip power is outstripping the power budget. And therefore we have very little left for doing compute, and even less left for doing compute if this does not doesn't get taken care of. Photonics is a big hope here, and we actually see that if we can actually use photonics, we can actually bring this efficiency of data movement much better under control. This is a work that we did, and some work that we've done in the context of a DARPA project with IR Labs, which was published a couple of years back at Hot Chips. And you can see here we are now looking at less than 5 picojoule per bit, serious bandwidth, good enough bandwidth of half terabyte, but much more importantly, the latency, electrical latency of sub 10 nanosecond. If you add to it the protocol latency of MPI, we see a line of sight to somewhere in the range of sub 100, significantly sub 100 nanosecond. That will be a 10x over where we are today, right? An order of magnitude improvement in the networking latency end to end. And the research is continuing because there's still electrical component in these. If we can bring that and integrate it much better to get rid of that electrical component, we'll see further improvement. In our research project in lab, plans to bring it down. The bandwidth goes up to terabyte per second, but the latency goes down to picojoule per bit or sub picojoule per bit. And here lies the hope. This will be disruptive if you can do that. And so we'll then have 10 to 100 nanosecond MPI end-to-end latency, and that will be 1 to 2 orders of magnitude from where we are, which should make a big difference. So now, and no architecture conference is complete without talking ISA. So now let's talk software. We have talked about hardware architecture part. Let's talk software, and we'll start with the lowest level of software stack with the contract that machines have with the hardware, quote unquote ISA. The AI is what it is today primarily because of tensor algebra. That's the algebra that happens and needs to happen most efficiently, needs to be abstracted most efficiently. And the opportunity in here for us is to really figure out what is that support for tensor algebra. Currently, it's done through libraries. We are in the jail of library, and these libraries get optimized, are derived for every neural network that shows up. It takes and by humanly optimized for all these accelerators that are there today, different CPUs, GPUs, and FPGAs. And this is an M by N problem. It's not scalable, and this is why ISAs were discovered, right? So can we now revisit our ISAs, which are kind of failing to compile these networks, and therefore we keep looking at Ninja Coder libraries. If we can figure that out, this M by N complexity that we are talking today can actually become the M plus N, right? Which will be a big improvement. That's what we have done recently in our paper, again, that's cited through a proposal called of tensor ISA. How do we, now remember, this is not about deep learning. This is about tensor algebra. So and tensor algebra gets used in HPC and definitely in AI quite a bit. So how do we offer first class citizen support for tensor ISA is one of our proposals. And this virtual tensor ISA, let me just enumerate the design principles that we used for this tensor ISA proposal. Each TPP primitive is a math hop, right? It can be unary operation, binary operation, or ternary operation, right? With one output, and all the outputs are 2D tensors. You can do higher dimensional tensors by just looping around them. Okay, so you have a nice separation of concern where all the polyhedral transforms are separated from this lowest level layer, which is closest to the hardware. These TPPs are all specified memory to memory operations, no register business. That's why we call it virtual ISA, which makes it much easier to move from platform to platform. And they have declarative semantics. So all the underneath stuff, the optimization for SIMD, SIMT, and etc. can be done underneath. Okay, they are composable. So you can do through register fusion, we can do producer consumer transform. The composability is super important. Finally, the precision is dealt in the most flexible manner. You specify the precision for your input, for your output, and for your compute. So you can have input in bfloat 16, computation in int 8, and output in AP32. You get to choose. So with this, we are seeing very encouraging results. Here's one. I'm personally not aware of such a result where a single source code across CPU architectures from Intel CPU, AMD CPU, ARM CPU is delivering architectural efficiency, which is meaning peak flop to realized flop, higher than anything we have.
That kind of portability we have not seen so far, but we are seeing across the board in these ResNet kernels. And if you look at the paper, you'll see data not just at the kernel level, but at the benchmark level and more. And we are now working on a tensor compiler that can actually compile it down to ISA and beat the Ninja coded libraries. So now let's move to the highest part of the stack, right? The highest part of this programming stack, software stack, which is where we're talking Python. Why Python? Because the choice of we don't have the choice of in the world of deep learning, right? It's pretty much made for us. Made for us in the sense that data scientists love Python, the language that's already spoken for, and it's the productivity of Python that really excites them. And interesting to note that while they love the productivity of Python, which is very MATLAB-like productivity, they're looking for performance more than a typical HPC guy. So someone who's looking for more performance than any HPC guy ever asked for, at the same time has a willingness to learn a new CUDA or Java or MPI is non-existent. So that problem becomes very, very hard as to how do we meet such need. But that's why we are there. That's why we are here. So how can we, and what's missing in that Python? Remember, let's go back to tensor algebra. From tensor algebra, what's the big data structure, the most important data structure? It's multidimensional array to represent these multidimensional large tensors. How do we offer support for multidimensional array as a first-class citizen? Distributed multidimensional array, right? And this is nothing new, right? What's new here is the fact that we cannot just be supporting dense arrays, but we need to support sparse multidimensional arrays, right? And dense array problem has been solved before. Distributed dense arrays, right? Large distributed dense arrays. First to handle it was Linda. So we talk about Ninja Gap today. There was no Ninja Gap then. The low-level coded message processing primitive performance was roughly the same as it came directly from Linda. Linda offers support for this distributed arrays indirectly through these 6 tuple operations. And this is a paper that Tim Madsen in our lab published many years back, 92, right? Long time back. So this was a good solution, right? And in fact, and had that one-way communication that is a characteristic of MPI, pre-MPI days. Global arrays built on it. And they made that, the problem with Linda was that when you're trying to reverse engineer the performance issues with your code, it was very hard because the support for dense arrays was implicit. Linda made it explicit. So it's explicitly exposed distributed arrays and it still had one-side asynchronous communication protocol. What made global arrays such a big success was really the last bullet that's noted here, that the programmer no more had to worry about translating global indices into local and plus some offset in there. That not having to worry about that made the programmer's job much easier. And this last bullet is what was at the heart of productivity, and we had good performance productivity for large distributed arrays. But let's talk where we are today. The biggest challenge that we have today, that while that is good, we have to deal with sparsity. Sparsity is job number one. And that makes everything much harder. So what we're doing now, we have a line of sight to actually being able to deliver this or build a solution to this through the software stack that I've shown a blueprint of. At the lowest level, we're supporting it's still a global address space. That's where it's super important, but it's partition global address space. We're building on PGAS, and we are providing these distributed data structures, which will hopefully be over time machine learned. And this work that we are doing with Professor Tim Kraska on learned index and learned data structures. We add on top of it algebra, a full algebra support, just like the databases have had for relational algebra. This algebra will have the support for these distributed data structures, which graphs like semi-rings and allowed values and operations. So we support all of this. When we do this and embed it in Python, we'll have Python-like productivity, but a performance of quote unquote the best we can get. So this is our blueprint for how we can offer performance, portability, and programmability for large dimensional sparse arrays. So, and it's a serious problem and serious issue that must be addressed. Why? Because right here at ISCA in 2012, we published a paper that did and get a lot of attention on how do we bridge the Ninja Gap using traditional programming methods. And it was published in 2012, and then it was republished in Communication of ACM in 2015. And the gap that we talked about then, which was already worrisome, was of the order of 100x when people were still writing C++. Not anymore. Now we're talking Python. That same gap with Python of a Python written gem versus Ninja optimized gem is a 60,000x gap. So it's a huge gap now. It's a much bigger problem. And you have to tackle it because the people who are moving into the programming software world are these Python programmers and data scientists, not computer scientists, not computer engineers. So this is a serious problem. We have been thinking about this. This has taken us a lot of sleep time. And it's compounded by the fact that in general there's a shortage of software talent, and this though the fraction of those who are willing to have such have ninja interest is much smaller. So the traditional approach to solving this problem of doing a very ninja hardware software code design, cache tiling, blocking, and optimizing, manually writing code is not scalable, and certainly not scalable in the context that we are in today. So how do we solve this problem? What is at the heart of it? When we thought about this some more, we realized that the key the crux of the matter here is the fact that our abstractions. Now, it all goes back to abstractions. Architects are who we are because we come up with the best abstractions in industry. Long time back, and that's we had a review of our project, of Minicode project with Professor Hennessy, and that's what he observed. He said, look, when Fortran was discovered, we had the right abstraction, and that's what made us so much more productive as opposed to writing assembly languages. And we need a similar new abstraction for these parallel workloads and parallel architecture, the era that we're moving in. And we have moved in deeply in this era, but we still have not found the right abstraction. And we need to rethink through. And the current tasks that programmers do is all jumbled up, right? Meaning the problem that you try to solve, the user's intention, the algorithm development, the data structure, the implementations for a given machine, it's all jumbled up. Can we come up with a new abstraction, a new separation of concern? And this is the discussion that we have been having with thought leaders in the industry. And we published this paper with some thought leaders at MIT, and more importantly, Professor Josh Terenbaum can be considered a father of AI. And this vision paper actually lays this blueprint for how we can think programming looking ahead, where we separate intentions, you and I, as expert in some matter, some field, will only express intentions at a high level language. And after that, the algorithmic, the choice of algorithm, the choice of data structure, and its optimized implementation on a piece of hardware will all be done increasingly by machines, or be separated. That separation of concern, like the halide has. And the reason we can do this and hope that this can be done by machine is why? Because look at the GitHub repositories, right? The training ground for these is immense. The GitHub repos used to be only 33,000 in just 2008. And today, more than 200 million repos, GitHub repos. So we have inside Intel, huge repository of code written by us ninjas inside Intel for our various architecture. This code can be used to train the machine as to what really is, quote unquote, a high performance code. And we said, look, if this sounds like a nice vision that we can all lose our job and machines will program themselves, can we test it? Same way, when someone probably had the vision of machines driving cars, they first said, let's challenge the machine. Can machines actually even see a cat different from a dog, from a tree? And can they find similar cats? That's why we put it to test by saying that, let's see, can machines actually understand what a code means and find similar code? That's a simple test, simple ImageNet-like challenge for machines. So we have put that vision to test through this similarity search, that can machines find good code, similar code segments. And so what we do here is, again, the same thing, like the inductive bias I was telling you, that first learn that we come up with a good data structure called CAS, right? Context-aware semantic search. There's a context-aware tree where we try to capture the program representation, the code representation, and this learned representation is then used to train through a whole bunch of training data on a neural network. We have tried different neural networks, graph neural networks, and DNNs. And once you're trained enough, we test it out, that how good are we, right, in finding these code similarities. And I'm very happy to let you know that where we are today, after testing on more than 19 million lines of code, more than 350,000 C++ programs, hundreds of unique classes, our MISSIM, our machine inferred similarity system, is now beating everything in industry that's out there. Everything. code to Vex, code to sequence, NCC, Facebook's Aroma. In fact, not just us, but it's being noticed just this month, IBM's paper on CodeNet actually showed that MISSIM is outperforming Facebook's Aroma CodeNet by more than 4 to 5x, 4 to 5 fold. And Andrew Ng blogged about this also. So point being that we actually, machines have passed that first test of a similarity test. They can actually find similar code segments, which is immensely powerful, because then you can actually replace a naively written code with a very high performant code equivalent without ever having to code it. So this gives us hope that we can actually design systems with AI rather than just for AI, seek AI's help in designing for itself. And after all, hardware is only software. So this will help us everywhere. And you probably heard quite a bit on AI augmented chip design. This was a Google claim earlier, improved claim this past week on using AI for better chips placement and route and better chip design. Internally, we have not published this stuff, but I'm showing you some internal data here that we have internally also. We noticed the same thing, that you can clearly see that it took a little bit more time, but we have a better solution for better layout, 14% smaller block area for very complex chips, right? So the turnaround time of 14 weeks versus 9 weeks is huge. Yeah, it takes some more cores, but that's not a problem, right? We like to have such good use of compute. But the fact that the turnaround time is going from 14 week to 9 week is supremely important to us, right? As chip companies, and it's not just one place; it's across the board. When you look at machine learning enhanced optimizations for our sub 10 nanometer technology node options, as you can see, it's ultimately all non-convex optimization problem, right? Complex optimization problems. As you can see, wherever we are, the blue parts of it, wherever we are able to apply machine learning, we have faster convergence. We have faster traversal through that search space, more efficient traversal. And therefore, end-to-end time is improved. And it's not small. It's actually very significant. More than 10-fold improvement in turnaround time. More than 10-fold improvement in turnaround time when we're able to bring in machine learning augmentation for our processes. As you can see here, when you're trying to improve the total negative slack. That measure of negative slack is how long it takes to achieve timing convergence. You can see we constantly, these methods improve towards a better negative slack and reducing total power, that red arrow that I've shown, and up to 10x improvement in total turnaround time. And not just for chip design, but in general for such optimization problems, we are now able to do optimizations and performance tuning at scale. Right, because as you can imagine, these problems are 10 raised to many hundred optimization complexity-wise, because there are that many variables which need to be learned, the knobs that need to be tuned for getting the best performance. And this is where we're using increasingly Bayesian optimizations to have a much better, faster traversal through that search space. And it is yielding productivity. I'll just show you some examples of this. We have an internal project, POC called Tuna, which does this machine learning augmented tuning at scale. And the default configuration that through a lot of ninja human work was the red dot. And you can see we learned much better operating points for this network function virtualization and much closer to the Pareto curve, which are points which are higher performance and maybe somewhat higher power, but points which are roughly the same performance, as you can see, but significantly lower power, or lower power, lower performance, but still much better performance and not and significant, but even better power. So such things, we recently published this paper with Professor Christos Kozarakis in the specific context of this Death Star social network benchmark. Again, as you can see, the default point is that red cross, but we obtain much significantly better results by using our AI augmented traversal of the search space. And you can clearly see that this improved things quite a bit, right? Much better performance, 6.3x better throughput. And yes, it did require more resources, but still significantly better, and not something that humanly, manually we could have done. It would have taken us a long, long time to find those orange triangles, but we could do that in real time thanks to the help of AI. So AI is helping us. And we are actually seeing, and if you go in the specific, rather narrow context of AI itself, the AI workloads themselves, the entire deep learning training is nothing but a long compilation process. At the end of that comes out a code, right? You feed that compilation process by just examples of images, right? Good or bad images, right? And the network gets trained, and after maybe many days. But at the end of the training, at the end of the compilation process, a piece of code, that black box, maybe a black box, but it's a piece of code. You can now use it to find cats and dogs, the problem that you wanted to solve. So in the specific context of machine learning, we have been also applying AI for that AI, meaning deep learning for deep learning, meaning deep learning in the hyperparameter space, which so far has been manually traversed and managed. The first use of this was our paper. I think we didn't call it AutoML then. I mean, but this, I believe, was the first use on industry or demonstration industry of AutoML technique. We used deep learning for deep learning in the hyperparameter space, and you can see that our DNGO, our neural network in the hyperparameter space, beat all the manual methods for all these different machine learning experiments. This is the work we did with Professor Ryan Adams at Harvard, and was published in 2015. And of course, we have come a long way now. It's a very popular topic. And as you can see, the machine-driven search of that neural network, where you can have an ensemble of these and finding the right structure itself, so that you capture the biases, inductive biases correctly, and then you train it. All of that done automatically by machines, and it's actually yielding performance better than non-deep learning approaches, better than manually designed deep neural networks. And the speedups are huge. I mean, at least the headline of the paper says up to 2 billion times acceleration. But bottom line being that in the narrower context of AI itself, machine learning is already showing promise in terms of actually programming for itself, finding its own network and finding its own code for it. But if you can actually deploy it and understand it in this larger context, I think we would have come a long way, because we go back to this blueprint I showed you for the software stack we have in mind, which would be hopefully deliver the best portable code, performant code, and productive code across platform, right? The first two layers of it, the high-level API and algebra, is the only thing that will be exposed. Underneath, everything would be learned machine-wise. Machine would be mostly machine learned. I didn't get to talk much about our work in AI-driven compilers, the cost model, the transformations of loop transformation, all the polyhedral stuff, as well as the Ninja code generation of the right data structure will all be done automatically. This is like, again, I said, the work we're doing with Professor Tim Kraska, learning these data structures, and the compiler work that we're doing on ourselves should help us, should make it possible for us to deliver the stack that we're talking about in a performant manner, all machine programmed at the bottom, and so that we do this nice separation of concern, where users are only exposed, data scientists are only exposed to things, the neural network and maths that they are very capable, are much more interested in handling that interface. And if we can do this, I think we would have come a long way by actually designing the right system for AI, which can scale with time and actually will be largely designed by AI with the help of AI. So here I sum up the 10 opportunity, what I consider as 10 opportunity pillars for AI, where you and I can have a much better impact, much bigger impact on industry. If we can do these 5 things which make systems better for AI: sparsity support, memory technology support for the large footprint, large working sets that we now see for these embedding structures, tens of terabyte per second bandwidth, tens of gigabyte capacity, exploiting, leveraging photonics for really cutting down the energy per bit, energy most efficient, and delivering much more efficiency in data movement, virtual ISA abstraction that offers portability, supporting tensor as a first-class citizen, and this distributed performance with a Python-like productivity. That's very, very important to keep the productivity angle in mind. And systems will get help from in this design mission by AI itself. Machine-aided code debug, which I didn't get a chance to talk about. I've offered the reference, and machine learning-based compilers, which I only alluded to, also have added a reference. But the 3 things I did show some data on: AI augmented chip designing and tuning, and code similarity search, and reasons we believe in machine programming. So if we can make these 10 things happen, I think we would have come a long way in our mission to build better systems for AI. So here on my last file, I'll summarize and then be ready for your questions. AI, machine learning rather, will pervade every aspect of computing, from ALUs to data center. I've rarely come across a workload that has so much of impact on everything we do. the numerics of ALUs have already been revisited, right? We finally learned bfloat 16 and such things, all the way to how we build systems of tomorrow at the scale of data centers. So it will change both what we design and how we design. AI will redefine the core of general purpose computing. This is where cycles will go. This will be general purpose computing. And computer architects therefore have to sign up to deliver this unprecedented CAGR that it's seeking, right? 10x per year, doubling every 3 to 4 months. And we need to be able to deliver to that CAGR and not shy away from the tougher ask here, that not performance, but performance productivity should be job number one, because we'll be judged in the courts of data scientists of tomorrow, not the software engineers of yesterday. And if the secret, on the other hand, is the same that we've always known. It's about building balanced systems. No point in building and bragging flops if they can't be fed, both north, south, and east, west. So the capacity, bandwidth, and networking have to be balanced, and that balanced system design is still at the heart of it. And machines, yes, will increasingly design and program themselves. With this, I'm done and ready for questions.
Thank you, Pradeep. That was a great talk. And I have quite a bit of questions here, so I'm going to get started right away. So somebody asks in the audience, could you place your concept of the architectural abstraction in the context of current GPU and TPU solutions? Do you expect this approach to outperform those for current and upcoming workloads, and why?
Yeah, so we are working on it. So far we have actually shown and seen how we can abstract and go across and deliver performance portable code across CPUs. We're internally also looking at our GPUs. And then we also going to look at our own TPU proxy, namely the Havana. So we have internal plan of looking at the virtual tensorizer that we just talked about, demonstrate that it does deliver performance productivity across all of these, right? And we have also had this conversation. We are having this conversation with industry leaders, you can imagine, so that we can together be looking at this. The piece of code there and everything in TBP is all open source, so folks can take a look. But absolutely, that's the idea.
Is there, perhaps you're not ready to share, but is there anything fundamentally that you envision that might be the tipping point there in your proposal versus the way that they do things today in the GPU and TPU world?
No, I mean, I don't make comment because we haven't really quite demonstrated the extension of it. We have demonstrated further across our CPU platform, including, like I said, ARM and non-Intel CPUs. But we are now at a point where we can take it to GPUs and then soon the next one. So I don't want to honestly speculate what we have learned in that process yet, but it's a very active project inside Intel.
Great, thank you. Another question is, do you have hardware support for sparsity in current or upcoming Intel designs?
Yes, so we will have hardware support. We do, but we will have, we have had hardware support along the lines of gather, scatter, and such things. But for deep learning, we will have first initially structured sparsity support, which is already out there, right? And GPUs also. But like I said, that doesn't excite us. Our biggest, the harder task here is support for unstructured sparsity, which, like I said, is the higher hardware overhead for it. I cannot comment on our product intercept, but we stay inside Intel primarily for that reason only. So we are working to get our research on unstructured sparsity support that I just talked about into our products.
Thank you. A related question by another audience member. Machine learning workloads often have no more than 90% sparsity. So what do you think about using dense representation and using special hardware support to skip those ineffectual computations transparently?
So that's what these hardwares do, right? Even though that 90% you talked about, if you do the math, right, it does still offer a room for significant improvement and a significant speed up, right? To doing those, to be able to not just do those zeros and later ignore them, but not to do them to begin with, only do the non-zeros. So there is that's what we're talking about, doing it transparently. And that's, by the way, that's a key. I should have mentioned there are all kinds of solutions out there. The reason we shy away from those sparsity support solutions is because it changes the recipe of how you train. And that becomes, the bar is much higher when you're changing that recipe. So it should be done transparently. And that's really the harder ask here. And only to that extent we'll succeed. Otherwise, we'll publish papers.
Right. Another interesting question. So going to your Tensor ISA, do you think that it could port well to the FPGA world, support FPGA programming?
Okay, yeah, so that is a good question. And honestly speaking, no, we haven't gone that far yet, but something to look into, yes.
Thank you. Another question about the Tensor ISAs. So do you, one of the arguments that you made, if I recall correctly, was that, this new abstraction allows you to generalize further rather than, chasing the next algorithm by doing application-specific support. How far do you think that takes you? Does it take you to very futuristic workloads, for example, that are way beyond neural nets?
Yeah, a good question. So that's what we're testing out by, so the paper, if you see, we are talking graph neural networks, and we coded all the distributed GNN paper you saw, the results I showed very early on were all done using TPP. So we are looking at GNNs and attentions, NLPs, and today's stuff. Because at the heart, we are talking tensor algebra support, that's where we have our hope, quote unquote, that this will actually go on and on much longer, right? We can last much longer because we're actually talking about how do we do tensor algebra right, as opposed to a specific workload, right? Okay, so that's the reason for believing this. Okay.
Great. I was very interested in the part of your talk that was talking about using AI for optimizing the system, for system tuning, right? And so I wanted to ask you, is that if that is a good use of AI, do you envision that happening purely on software, or do you envision using some silicon to help out tune the system itself? In particular, even possibly some of the hardware that was originally intended to speed up AI actually ends up helping itself.
Yeah, quite possible. So we'll only find that out, and now that we are practicing it, right, we will learn how to speed up that tuning through hardware support. I mean, we have had all kinds of ideas on mining performance counters and such things through hardware support, right? But we're not quite there yet. At this point, we're just practicing that so that we can learn where the bottlenecks are to make such optimizations happen even faster, even quicker sooner.
Thank you, Pradeep. Other question, you have a lot of questions here. Other question is, do you think that the domain languages such as TensorFlow or PyTorch would interface nicely with that Tensor ISA in the future?
Absolutely. We are working with those authors to make sure that happens. Absolutely. Because the whole goal here is to deliver compiled performance to machine learning. If you've seen the Google paper on something called machine learning systems are in a rut, that's what it talks about. We need to liberate machine learning, deep learning from the library jail, right? So that you can actually come up with whatever neural network you want, capsule nets of tomorrow, and not be at the mercy of someone humanly coding few library functions. Just get compiled performance. That's what architects and the success of computer architecture has been all along. That's what we were hoping to get to. With the help of Tensor Compiler, this new algebra supported dimensional arrays at the language level and all the way down, support for same tensor algebra at the lowest level ISA level through a portable ISA.
Thank you. So moving on, when you were talking about general purpose scalable that you can project architectures, you were mentioning also the memory side. So on the memory side, somebody was asking, how do you scale sparsity? How do you connect this need for higher bandwidth and at the same time having this sparse nature in your workload?
Yeah, I mean, look, if the world was really ugly and sparse, then like I said, even with the Stephen Mallet observation, we have no hope, right? The hope lies in the fact that there is an order in the disorder, right? But it's very compact. Remember, ultimately, when neural networks are done, the trained neural network is very small, nothing like that gobs of stuff we started with. So there is something there to be learned which is very compact. It's just that it's all over. Those lights are all over the globe and we just need to bring them into the cache line, right? So that's where lies the hope. Now, of course, sparsity, I showed you data that there is a power law. Even in this very random looking stuff, there is a power law. That's the reason why we are talking about this large working set. When you don't capture the working set, you see random, you see gups. But when you capture the working set, it's much better. It's like, aha, it's like suddenly everything's so nice. But there is a working set, it's much larger working set. Good part is we can actually get there with technology, memory technologies that are upcoming.
Very good. Somebody is asking, well, first he's saying, thanks for your very inspiring talk. Then she says, you talked about many opportunities for AI, but could you please comment at the end of the day, what are the systems problems that you envision coming for which AI will not be good?
Our hope is to keep AI, like I said, this hen that keeps laying golden eggs, right? So that we are all happy. There's insatiable demand for compute, and we keep doing it. But
I predict that somebody's thinking, all right, if everybody's busy with AI, maybe I want to focus on beyond AI.
I know. So there is the part that none of us talked about, the last part, then the fifth dimension of my 5 is all about ensuring AI stays good. Okay, now that's where I see the biggest problem or biggest challenge, but it's beyond the description, beyond the scope of this talk. But that's where I fear, and we have to make sure that the ethical aspects of AI stay under check. And it all happens in the public domain.
Very good. All right, we are out of time. I want to thank Pradeep very, very much for agreeing to be one of our keynote speakers. It was a pleasure to hear your talk. I encourage everyone as we move out of COVID to take time to visit his team in California. It's a fantastic team. And I will see everybody else at the award ceremony. Thank you, Pradeep.
Thank you.